All right, guys. So we're gonna get started. Let me move this over here. So what we are going to do, guys, today. Hold on. I'm still trying this out. There we go. So today, day one, what we're going to do is we're going to go over some geology notes that'll help you guys out on the assignments that I've posted over the last couple days. Remember, I've seen a lot of you guys give me emails late at night. Remember, you don't have to, they're not due until Sunday, next Sunday. I don't know, hopefully I made that clear, but I assign them on Sundays. I think I put stuff up on Saturday, but I sign everything on Sunday, and then you have 7 days to get it all done. So you'll have two due dates or two assignment due dates each week. So yeah, I don't see anybody in yet, but the opportunity still stands as far as we're doing this. I'll be doing this live every day, like I said, for a couple, 15 minutes, and then I'll post the recorded video of what we're talking about online here and later. The only thing that you won't be able to see on the recording is the comments that you guys post, but we'll talk about maybe setting up a Google Meet. I'll show you guys how to do that. I'll kick out an email. So just in case you can't make this stream, that's fine. This is just another opportunity for you guys to be able to talk to someone and actually have some stuff going on. So what we're going to start with, though, is we're going to start with the geology part. Now, I've already shared this PowerPoint out with you. I'm going to go as sort of delayed as possible because I know some of the stuff takes a while for it to load. My computer's not the best. So what we're doing is we're talking about Earth's history. So Earth's history, hold on, I'm just making sure the stream's catching up. Alright, so we'll try this. If it doesn't work, the recorded version will be better. So, Earth's history. We're shifting out of biology. I know we were going to finish up with bio at the end of the term, but we weren't able to do that just because of this whole craziness and lockdown. So we are now moving into the geology portion of our science class. So to start everything off with geology, we got to talk about the history of the Earth. Now, I know I've talked in class about how old the Earth actually is. Our current estimates are in the 4 billion years. 4.6 billion is roughly kind of where we're at. This picture here shows you kind of like a little spiral timeline of how long we've been here. And if you look at this, if this was to be stretched out, we're at the very, very tip. Like human existence has only been around for about 500,000 to a million years. So we haven't been here very long. Then you have the dinosaurs, you have all these other organisms, but life didn't really start showing up on the planet until about 3 billion years ago with plants and stuff like that. We talked about that a little bit in bio. So we'll get going. So one of the most important things is, how do we know the Earth is this old? Well, the Earth is 4.6 billion years. How we know this is that we can take rocks and we can look at what's inside of them, and we can take the stuff out of that, and then we can date that. We know that there's little chemicals and stuff that are inside of the rock that we can see as they deteriorate, as they go away. We can count and measure how much is left. So if you have, let's say, this pen here, you got this whole pen, and after a certain amount of time, half of the pen decays away. So now all you have is this left, or pencil. We can measure how much is left versus how much is decayed, and we can identify how long that takes in order to decay, something called a half-life, something we'll talk about here in a second. But that's how we know how old these rocks are. And we can see rocks all over the planet. The oldest rocks that we know that we have found so far that have been undisturbed are in Africa. They're in the billions of years old, and they are from one of the earliest forms of the continent, which is kind of cool. So the first person to kind of get an idea, see, about 200, 300 years ago, the majority of the people thought that the world was about 6,000 years old. And that's what religious scholars taught. That was the general thinking, because 6,000 years is a very long time, especially when human beings at the time only lived 40, 50 years at the most. Some made it to 60. But this guy in Scotland was walking on the hills, and he noticed these rocks that were layered like this. You see the lines going back and forth. But then he also looked over here and saw rocks with layering the same pattern, but they had a different direction. And what he figured out is that this must have caused something must have caused that rock to shift. And by shifting, it causes the rock to be really, really old. And so that whole 6,000-year-old thing kind of went away. And he knew that it takes a very long time for a rock to form. And so for it to form like this and then shift and then stop forming, that means it's really old. And the stuff on top of it would form. So you can kind of see this picture where you've got rocks forming in this direction, and then you have rocks forming in another direction, and they're on top of each other. That means this rock down here is actually angled itself, and then new rock has been formed on top of it. I don't know how well these videos will work, so we'll try. I'm just going to click here and see. Oh, maybe not. Try again. I don't think it's going to let me, so we'll skip the video. So a term that he came up with was something called uniformitarianism. It's a very, very, very big word, but what you need to know is that the stuff that happened in the past continues to happen today. That's what uniformitarianism means. It basically, we know that the stuff that happens today happened back then, therefore it happened before that, and it constantly is happening all the time. So it may be a little bit different, but it still happens. And how fast it happens or how slow it happens can change, but it still happens. Volcanoes erupted in the past, they're going to erupt today. Rock forms the same way today as it did 4.6 billion years ago. So we know that that concept is going to be the same. And a way to remember this is the word uniform. So the word uniform is in it. Uniform means you wear the same thing. So uniformitarianism means it constantly is the same. So I'm going to go ahead and switch the slide. So like I said before James Hutton, the idea was the Earth was about 6,000 years old. Most geology was thought to all have formed at the same time. Like it was all created at the exact same time and it happened at once. He then, when looking at those rocks, realized it took millions and millions of years for that to happen. And it kind of went against everything that was out there, the known science. So it was it was hard for him to get in and be told about it because, well, you have to, what's the best way to say it? You have to be able to get credited by other people in order to be a valid scientific statement. But if everybody else believes that the world is 6,000 years old and you're coming out and saying, oh no, it's not 6,000 years, it's millions of years old, they're going to look at you like you're crazy. So there are two different types of age when we talk about rock. We have relative age, which is basically an example of this would be I am older than you guys. So relative age is I'm older, you're younger. It doesn't have any specifics. It just means I'm older than you, you're younger than me. We can look at this and we say, hey, we know the rock here is younger than the rock here. Now we don't know the age, but if we can figure out the rock here is this old, we can kind of figure out how old this rock is. But it's not very specific. Another word for those layers are called strata. So here's a couple examples of that rock layering. If you look at Cincinnati, Ohio, I don't know if you've ever driven in this area, but I have. It's a cutout where they went to build the road, and you can see the nice lined layers of rock. Well, each one of these layers is strata, and each one of these layers formed over time, over millions of years. If you go to Denver, you get the exact same concept, but now something has caused this rock to shift and tilt. And you have the exact same pattern as you do over here in Cincinnati, but over here it's striped. I can't even pronounce that. I'm not going to try, but you can see how the patterns are sort of all over the place. So what happened down here is you've got this nice layering effect, and then you have another rock that built on top of that, and then at this point something caused this rock to sort of peak up, whether it was an extrusion, volcanic activity, something like that. And then you have all these different layers. And then here, an example of Hocking Hills, you can see the rock layers as they build up along the side of the hill, the cliff. Now, this next law is another real sort of guiding force for geology. And the big thing about it is it's called the law of superposition. And that basically means that anything that is on top of something is younger than it. So if I take this thing here, and I have a whole bunch of layers of paper, the layer on the top is going to be the youngest. The layer on the bottom is going to be the oldest. So superposition just basically means the stuff on top is younger than the stuff on bottom. So you really have to remember. All rock, well, not all, the majority of all rock forms in something called sedimentary environments. Sediment, just like in the ocean, is underwater. Little particles will rain down and then lay on the bed of the ocean. And then over time, all those little particles of sand and little dead organic like shells and stuff like that, they will all start to compress and eventually form into a rock. That's sedimentary rock. That's what we're going to talk about in the future. That's how most rock is formed because we have so much water on this planet. The rock that you see in those layers, like we did in the previous slides, those layers are formed from stuff falling from water down and settling at the bottom. That's how most rock is formed. And so as things settle, the stuff that settles on top is obviously younger than the stuff that settles underneath. Let's see. The video. We're going to try it. I don't like it. But
hey,
we'll see how
we are ready to demonstrate superposition. So one way to think about superposition is your laundry bin at home. So the oldest laundry, the stuff you wore the longest time ago, is always at the bottom. The stuff you wore just yesterday is on top. So we're going to demonstrate it with shirts. So we have our whole wardrobe for the week. Here's our Monday shirt. Oh, God. Monday shirt, bottom of our laundry bin. Tuesday shirt.
You're being neat. I'm not being neat.
Well, it's easier to see the layers.
I'm not neat.
Tuesday shirt. Wednesday shirt. Look at her pile.
Hey, nice shirt.
Oh.
You matched me.
Well, you know.
How'd that happen?
So, Wednesday. We're on Wednesday?
No, this is Thursday shirt.
Oh, no, Thursday shirt. Nice shirt again.
Oh my gosh! This is so weird.
How
We
did
matched
this
the whole
happen?
week. Thursday.
Okay, they're cheating.
Friday!
You're in casual Friday mode?
Yeah, I am, yes.
Huh?
You can read the science teacher.
Yep. Okay, so there we go, class. If we look at our piles, so the oldest shirt, our Monday shirt, what do you know? On the bottom. This is the one we took out first. We deposited that shirt first. So we've got all of them in order. Our Monday shirt, Tuesday shirt, Wednesday, Thursday, and Friday shirt. They're all stacked up.
Now we need to do a whole lot of laundry.
Definitely. Okay, that's it, class. Hope you enjoyed the demo.
So yeah, that was pretty cheesy, but it gives you a good example of the layering of these rocks. So if you look at this, it's just an example of if I were to ask you what letter is the youngest, you would say F. The oldest would be A. Over here, you have the youngest to the oldest, same concept. A is going to be at the very bottom, F is going to be at the very top. It just shows you an example of what it is. The next concept that we're talking about is called the principle of original horizontality. Now, that is a crazy, crazy long statement, but basically what it means is that if you don't touch anything, they will constantly stay in this pattern. So horizontal means this way, right? So if everything stays this way, the process stays the same. But if you disturb it, if you tilt it or twist it, you're still going to see that same patterning, but it's going to change because that has been disturbed. So if you look at this picture here, you've got this fold because a fault has happened and caused that break. But you still see, here's the layering from here up to here, but then the fold starts a new layering process. But you can still see the layers, so they still follow that same concept. But because of that, here's the original, here's the new. That means this is older than this. So if we look at, we're not going to do this bottom one here, but if we look at this, the colors here are going to be your examples. Now, the very bottom layer is going to be this little pattern area right here. This layer is going to be the oldest. The next layer above it is going to be B. Then we're going to have A. And then we have this thing right here. This is actually an intrusion. It's a volcanic plume that shoots up and goes all the way to the surface. Notice how it goes all the way here. That's why we know this is younger than A, because in order to go through A, it had to be there. And then E is the youngest because E cuts through all the parts. It can't cut through anything if it wasn't there. Now that term is called cross-cutting relationship. The word cross and cut is in there. If you can't cut a piece of paper unless the paper is there. This fault cuts through the paper or cuts through the rock because it was there. So the fault has to be the youngest. Now, if E did not cut through, let's say it only cut through down here, it may not be the youngest at that point. So it's just an example of what you guys can do. This is some of the ones that you can get like really crazy, like what's the oldest, what's the youngest. We're not even going to talk about that one. That's just too difficult. Again, this one, super hard. If you want to try it on your own, go for it. Maybe I'll throw some bonus towards you. You can put your answers over here, or you can just type them down, something like that. Skip that area. Where are we at? We are at 26 minutes. We're good. We'll do a little bit more. So how do geologists determine relative age and what happened in the area? Well, you have graded bedding, cross beds, and ripple marks. So that gives you an idea of what's going to come. Graded bedding is basically you have normal grading, which the heaviest stuff falls to the bottom first. The little itty bitty pebbles, they're going to fall the ledges. If you take an ice cube or salt, let's say, if you take salt and put it in the water, it's going to fall pretty quickly down to the bottom. But if you fine grain that salt, it's not going to fall as quickly. It's sort of going to float really slowly down. So it's kind of how that is. Inverse grading, basically what happens is something has taken that rock and flipped it upside down. So you have all the big stuff at the top and all the little stuff at the bottom. That's not how things fall. We know that. If you take a big rock and a small rock, the big rock is going to fall faster than the small rock in water. So in this case, something has happened to that rock and flipped it upside down. Cross beds, basically that means you have bedding going like this and bedding going like this. When sand gets deposited, it usually goes at angles. Whether it's a current, whether it's just how it is. You have angles. The angle deposition as you go over time. You're just going to see those different angles. So, like you see in this picture, you've got this layering right here, but then for some reason something has caused this rock to shift, and then you get a different angling coming up this direction. So that's all that is. And then ripple marks. This just shows. If you go to the beach and you notice how like the waves, like really shallow areas, the waves will ripple over the water, and underneath you can see like these little grooves set into the beach or the sand. That's what those come from. So over thousands of years, those ripple marks actually start to fossilize or not fossilize, become stone or rock, and they keep that pattern. So you can see, like here, you can see the ripple marks. That tells you this was probably pretty shallow, or there was a currented area near this. So you know it was definitely underwater. You know it was probably in a shallower area. You don't get this in really, really deep water because you don't have the wind to help with those little waves. An unconformity, we're going to go pretty quickly over these. Unconformity is something that just breaks the geologic record. So if you've got the layers, like if you take this, you got all these layers in here, something went and broke those normal layering patterns. A nonconformity is basically anything. So you have a normal rock and then something that's not normal underneath it, whether it's magma or something like that. So if you look at this picture here, you see the layers, nice and pretty, but then underneath here you have all this like hot lava type of thing. So not necessarily, that's a nonconformity. Angular unconformity is you have normal layering on top, and then you have these angles underneath, and that's what that means is that lower level in this picture has shifted, and then stuff started depositing on top of that. A nice, easy way to remember that is angular unconformity. It means it's got an angle to it. And then a disconformity is that you've got these normal layers, but then all of a sudden you've got something that's just a little different. And how this happened was this layer, this brown layer at the bottom, formed normally. Then you have a nice flat, pretty flat line. And then this layer formed. Then this layer formed, but at one time, the ocean may have gone away, or it dissolved, or the rock was uplifted. And so at that point, this layer starts getting eroded. So it's no longer going to have that nice, clean line on top. But then eventually, after the erosion process, you have sedimentary rock deposit on top. The problem with this is that with this layer, you can't tell what's on top of it. Like, you don't know how long this has been eroded away. You can get an idea, but there's no way to really tell. So it's a break. It's very difficult to tell how old this break actually is. Cross-cutting relationships, that's what we talked about in that picture earlier. Anytime a fault or a line cuts through something, that means that fault or line is younger than the rock that surrounds it. You can't cut a piece of paper without the paper being there. That's what that is. An intrusion is anything that sort of comes up into the surface of the earth. Here's a picture of a fault, letter E. Here's an example of a fault. You can see where the crack line is, whether it was caused by an earthquake or something like that. And then F, that's your intrusion. That's basically magma coming up through the rock and then depositing or erupting onto the surface in this case. I think we'll stop there. That's about a half hour. So I didn't see a lot of people on the stream. That doesn't mean that you guys didn't try to get in. Maybe it just wasn't cooperating. We'll see how it goes. I'm going to send out, we'll try to do this through something called Google Meets if you would like. If that's something you guys are interested in, we can always try that. So I will upload this video. I'll be doing another one tomorrow. So let me know what you think, and we'll go from there. Stay clean, guys. Hope you have a good rest of the day, and make sure you keep checking online every day to see what you're going. So see you guys.